Welcome to Powered by Tesla.
Today, we are diving into a really weird but totally brilliant piece of engineering, the synchronous motor. This thing is a machine that basically runs on a whole series of fascinating contradictions. And by the end of this, you're going to understand why it's one of the most unique and powerful devices on our entire electrical grid. So let's just jump right in with its biggest puzzle.
Okay, so let's start with the central riddle. I want you to imagine a motor, a big, powerful one used for heavy-duty industrial jobs that has absolutely zero ability to start on its own. You give it all the power it needs, and nothing. It just kind of hums and vibrates. How is that even possible? And, more importantly, why would anyone ever build a motor like that?
And it gets even weirder from there. This motor runs at a perfectly constant speed. It is locked to the grid's frequency, no matter how much load you put on it, or it just won't run at all. It's all or nothing. It has zero starting torque. And get this, its most powerful feature has nothing to do with moving things. It can actually stabilize the entire electrical grid.
Okay, so to really get our heads around this, we have to uncover the secret of synchronism. And it all comes down to something called the magnetic lock.
So inside this motor, you've got two main players. First, there's the stator. That's the stationary outer part. When you feed it three-phase AC power, it creates this magnetic field that spins at a very specific constant speed. We call that synchronous speed. And then you've got the rotor, the part that's supposed to spin. We feed it DC power, which creates a fixed magnetic field. You can just think of it like a simple bar magnet that doesn't rotate on its own.
It seems logical, right? You've got a spinning magnet in the stator. It should just grab the rotor's magnet and pull it along for the ride. But that is not what happens at all. So what's the deal here?
Okay, so here's the problem in slow-mo. For a split second, the stator's north pole pushes the rotor's north pole away. But because it's AC power, the stator's magnetic field instantly flips. That same spot becomes a south pole, which now pulls the rotor's north pole backward. This push-pull happens so incredibly fast, we're talking 50 or 60 times every single second, that the heavy rotor, just due to its own weight and inertia, can't possibly keep up. It just sits there and vibrates.
And that brings us to the absolute key to this whole thing. The motor only works if the rotor's already spinning at the exact same speed as the stator's magnetic field. Once they're synchronized, the opposite poles on the stator and rotor just lock onto each other like incredibly powerful magnets, and the stator pulls the rotor along at a perfectly constant speed. But of course, getting it up to that speed is the real challenge.
So, how do engineers solve this seemingly impossible starting problem? How do you start the unstartable? Well, as it turns out, they use a very, very clever trick.
Meet the secret weapon, something called a damper winding. It's basically a partial squirrel cage, kind of like what you'd find in a completely different type of motor, an induction motor, and it's built right into the face of the rotor poles. This little addition allows the motor to pretend to be something it's not just for a little while. It gives it a temporary secret identity.
So the startup process is basically a two-act play. First, we leave the main DC power to the rotor turned off. We just turn on the AC power to the stator. Its rotating field interacts with that damper winding, and the motor starts up exactly like a standard induction motor. It accelerates, getting closer and closer and closer to synchronous speed. Then, at just the right moment, we flip the switch on the DC power to the main rotor winding, its magnetic field roars to life, and click, it magnetically locks in step with the stator field, pulling itself up to full, perfect synchronous speed.
Running at a constant speed is useful, for sure, but it's not the motor's most amazing feature. Now we get to its real superpower, the ability to actively tune the very power grid it's connected to.
Now, to understand this, we need a quick definition of power factor. The easiest way to think of it is just as electrical efficiency. An ideal power factor is 1. But a lot of machines, especially standard induction motors, draw extra reactive power just to create their magnetic fields. This drags the whole system's efficiency down, creating what's called a lagging power factor.
But this is where the synchronous motor is in a league of its own. Remember that DC current we feed to the rotor? It has a name, excitation current. Well, by simply turning that current up or down, we can control the strength of the rotor's magnetic field. And by doing that, we can actually change the power factor not just for the motor itself, but for the entire electrical system it's hooked up to.
Here's how it works. If we underexcite the rotor with a weak DC field, the stator has to draw reactive power from the grid to make up the difference. That gives it a lagging power factor, just like an induction motor. But, and this is the amazing part, if we overexcite it with a strong field, something incredible happens. The stator now has too much magnetic field,
and to balance itself, it pushes reactive power back into the grid. It actively starts to cancel out the lagging power factor of other machines, creating what we call a leading power factor.
This is the key takeaway, right here. When it's overexcited, the motor behaves, as one source puts it, like a giant capacitor connected to the power line. It's actively supplying the reactive power that other machines on the line are demanding. It goes from being a consumer to a producer of this vital electrical component.
In fact, this ability is so valuable that sometimes these motors are installed with no mechanical load at all. They're not connected to anything. They just spin freely. In this role, they're called a synchronous condenser, and their one and only job is just to sit there and improve the power quality and efficiency of the entire grid.
All right, so with all these strange characteristics, where does this motor actually fit in? Let's do a quick head-to-head comparison with its far more common cousin, the three-phase induction motor.
The trade-offs become really clear when you see them side by side. The synchronous motor gives you that perfect, constant speed and an adjustable power factor, which is amazing, but it's more complex, it needs a DC power source, and it can't start itself. The induction motor, on the other hand, is simple, it's self-starting, and it's cheaper for high-speed jobs. But its speed drops with the load, and it always hurts the system's power factor. They're truly two different tools for two very different jobs.
So you'll find synchronous motors where their unique strengths can really shine. They're super economical for these huge, low-speed applications like rock crushers and ball mills. They're absolutely essential for any process that needs perfect, constant speed. And, of course, they get installed in factories and substations specifically to correct power factor and regulate voltage.
And that brings us to a final thought. I mean, at its heart, this is old technology. But its ability to actively stabilize and support the power grid is just a remarkable feature. As our grids deal with more intermittent power from renewables and more complex loads, you have to wonder, could this century-old motor's superpower be more critical today than it has ever been? It's a fascinating question to think about.
Like and share this video. And don't forget to subscribe to Powered by Tesla.